So let's summarize what we have been doing. We want to compute study the analyticity properties of this integral, which is the bubble diagram. And it is convergent in Euclidean, or in Euclidean space. If you put some numerators, it will become divergent, but the divergence will be local and you can subtract it. Instead, in Minkowski spacetime, it's badly divergent. So we need to start from Euclidean, the Euclidean space. And that means integrate for imaginary energies. Loop energies have to be imaginary, external energies have to be imaginary, and then you rotate. Now the Wick rotation normally is thrown in a very superficial way in textbooks, but it is an analytic operation, or in this case a well-defined, unambiguous, non-analytic operation. But normally you have to treat it very seriously, because it means that you are computing your integral for complex external energies and external space momenta, actually, and complex loop energies and loop space momenta, and then you study what happens in the complex plane and check if you can perform the rotation analytically or you find obstructions. In this case, you will find obstructions due to these poles that are actually the poles that are responsible for the problems are those that are located in the first and third quadrants of the complex plane, because then you cannot rotate, and that's the difference between Minkowski and Euclidean. Anyway, we start from Euclidean space and then see what happens. So when you integrate in Euclidean, you will find this kind of integration path for the loop energies. And that is because if you start from two pairs of poles that are close to each other, so you start from external, so the red quadruplet moves around because it is dependent on the external energy or momentum. That's k minus p. So this is the k0 plane. And so if you start from p equals 0, the poles are superposed with the blue ones. And then the Wick rotation is simple. It's like that. The moral of the story is that the right pair of each quadruplet should be above the integration path, and the left pair should be above the integration path, and the right pair of each quadruplet should be below the integration path. So when they move around, you have to keep that, because you cannot cross the integration path. So even when the external energy P0 moves them across the vertical axis, it doesn't change anything. you cannot do this, for example. You naively make the Wick rotation like that, you would say you have this. This is not true. You have to think about it a little bit more carefully. And the reason is that you have to rotate every momentum at the same time, every energy actually, at the same time, so you can directly check that the Wick rotation in this case leads to this integration path, which is the right one, because then the non-local divergences that you would find in Minkowski spacetime cancel out, and they cancel out pair by pair. So this cancels this one, this, and this, etc. But if you integrate in Minkowski spacetime, you would split each pair, and then they will not cancel at all. So that's why Minkowski spacetime is not viable. But you have your own pinching in this case, because situations like this, so we have to check what happens about the violation of analyticity. And so you first perform the integral on the this kind of contour by means of the residue theorem, that each residue will give you a contribution. And then you remain with an integral on R3, actually we will see, of some integrand which is a rational function with some frequencies around, actually, so it's not a rational function everywhere, but there are some square roots. That's all. Square roots mean a lot for analyticity. And this function is analytic every time the integrand is non-singular for every k in R3. Or if you want to deform that domain, for any time it is non-singular for every k belonging to the new deformed domain. And you have to be sure that the deformation does not cross poles, singularities. So we studied the location of the singularities for k belonging to R3 and actually k belonging to some new deformed momentum. And the singularities are described by this equation, which is the same one we found for generic m1 squared and m2 squared. You just have to replace them with the two values that you have now with complex contributions. And then you find, for example, in one dimension, because it's unnecessary to, it's easy later to discuss more dimensions, you will find that the locations of the singularities in the loop space momentum kx as functions of the external energy, you could study them as function of the external energy and the external momentum. In the end, you will recover Lorentz invariance. So for the moment, Lorentz invariance is not true, but let's keep px fixed. So this loop external momentum fixed, and you just check, use p0 as a parameter. And then what you find is that, let's see if I, is that if you plot the location of these, these are all the singularities, well, one, then you have the minus one, minus minus, minus plus, you have several, and I can anticipate the other ones will give two kinds of surfaces up there, there, and down there. And then you will have the symmetric ones. But those are not interested. Well, first, the symmetric ones are symmetric, so you don't have anything new. And those that are up there are when you have plus plus or minus minus, so it's truly imaginary. You see, you cannot have a real contribution because, but this is real when you have one plus and one minus. It gives something on the real axis. That's not really. So the interesting case is this one. But you can check that the solution of this fills the entire region here, because you can solve this, and that's what we did yesterday for kx. And then you can check how kx moves when you vary p0 in the complex plane, kx plane. And that means that you would start from integrating on the real axis for the loop space momentum, but then you check that if you integrate on the real axis, the locations of the singularities are 2 points here that move like that. They meet somewhere there, and then they go down. And this is if you move on the real axis there, which means you take p0 real and growing. And if P0 is has a small imaginary part, then you find the two trajectories here. And you see that one crosses the integration domain once and goes and then exits, which is precisely here. So let's say that this is B and C, this is B and C, and so on and so forth. So here, for example, will be this point. Here it will be this trajectory. Here it will be this trajectory, and so on and so forth. So that means that if you insist integrating here, you have some pole that crosses your integration domain, you violate analyticity. Here you violate analyticity everywhere. The only thing you can do is when this moves, which means you get here, you deform the integration domain on the loop space momentum so that you do not cross this. And that is equivalent to shrink this surface into a half line, which is a branch cut. So instead of integrating on real space, loop space momenta, you will find that there is a deformation that keeps the result analytic everywhere in the upper half plane, everywhere in the lower half plane, but there is no possibility to keep it analytic everywhere, so there will be a branch cut there. But it will be analytic up and down. So that is what you have to do. Still, that does not solve the problem because those singularities meet here, and then after that, if you move along the real axis with P0, after that they are located on the integration domain, which we will call D, or in 3 dimensions it will be D3, it will be this one, times a plane. Every point will be a plane in the other 2 directions. And then you have the 2 singularities located on your integration domain D. So you have to tell me if this is your prescription or that is your prescription. Neither of the 2 is okay because both prescription would be type Feynman prescription. So this has become a branch cut, and then let's say this is with the deformed domain D, and the 2 possibilities correspond to circumvent the branch, the threshold from above or from below. But now there is a 3rd possibility. And the 3rd possibility is as follows. You calculate your integral like that. What was it? Kp with the wrong domain. And you do it for P here. Wherever you want. If you want your amplitude on the real axis, let's say we want this point Q. So you cannot compute it there because you are on the branch cut. You do not know how to compute it. You could reach it from above or from below, but which one? Which is the right answer? So, but we can compute it here. If you compute this integral with the wrong domain, what you find, which means that you go inside this surface, you find that there is a singularity we will describe the singularity in a moment, that is an integrable singularity. So you can, the integral has a well-defined value. But moving around this Q inside this region will give you a result that will be not analytic, because you have crossed. Not analytic with respect to the analytic function you find here in every other point. And not analytic even if you move it around here. It's not a second analytic function because there is a singularity everywhere inside here. It's a continuum of singularities in higher dimensions, only in 2 dimensions. The singularity is just on the boundary, but in general it is everywhere. Anyway, it's not analytic and not Lorentz invariant. Not Lorentz invariant. The reason why it's not Lorentz invariant we have already anticipated. It's because you cannot integrate on a complex domain for the loop energy and a real domain for the loop space momentum and hope there is, well, you can hope, but you won't find Lorentz invariance. However, what you cannot do is to compute it there after the deformation. So you compute it there before the deformation, and then you deform. You view this integral as a function of its own integration domain, and when you perform this deformation after, so you sit inside the region, you compute, you find the result that's not analytic and not Lorentz invariant, but it's a function of its domain, and then you deform the domain continuously from R3 to this, which means in 2 dimensions this. You even have an explicit expression for this. What you get when you perform the deformation is that in the limit you recover analyticity and Lorentz invariance. And actually there is a very simple way to describe the result, because what you compute by sitting inside, which will correspond to the value of your function in the bracket cut, is the arithmetic average of the 2 continuations from above and from below. That is what it is. So it's just the arithmetic average. It's neither of the 2, both are wrong. Both will describe an unphysical process, but the average of the 2 will describe a no process, a fake process, which will be fine from the point of view of unitarity. But the average of 2 analytic continuations is not an analytic continuation. It's an unambiguous, non-analytic operation. So let's describe this. So let's see what happens when we compute inside. The integral will be the integral of an expression. Let's isolate the singularity. Let us check how the singularity integrates out. And that means that we will have an integral on the loop space momentum k with a certain denominator times many other non-singular things, which we ignore for the moment. And the denominator is P0 minus the 2 frequencies. Let me check how I wrote them here. Okay, mu squared was, let us put mu squared equals 0, otherwise I don't have the formulas for non-zero. Then I have minus p, yes. And I call it d5 because I want to study at the same time the Wick rotation. So let me put a phase here where I want to move from complex so P0 is the Minkowski energy, but if I put a phase here with phi equal to 90 degrees, we will not need 90 degrees, actually we will just need a small phase because we will reach from above or from below, but we want to study at the same time the Wick rotation. So with the change of variables, you can check how this behaves, and I write it down. So first we call the modulus, the length of ks, the length of ps, then u will be cosine of theta, where theta is the angle between the two vectors. And then the change of variables is, well, here you will have an integral on theta and ks, basically, because there is an angle that is not phi, because phi now is the phase for the Wick rotation. We do not need an angle there, this kind of phi, because it integrates in a trivial way. Anyway, the change of variables is as follows. Let me assume P0 positive. Otherwise, you have to keep an absolute value or consider both cases. So sigma plus squared to sigma minus p squared squared plus eta ps sigma plus squared for sigma minus m squared, and u is equal to ps divided by 2ks plus eta sigma plus squared divided by 2 sigma minus m squared, where I have defined sigma plus or minus I forgot the definitions of sigma plus or minus. And we have to recover it in a moment. So we are changing variables from ksu. d3k will be the integral on ksu from tau eta. And well, we don't need this. Let me check. Yes, sigma plus or minus is what? Sigma plus or minus is p0 to the fourth plus or minus 4m to the fourth. p0 to the fourth plus or minus 4m to the fourth. Well, you can check it. And then you will see that this integral, after integrating on the phi angle, gives what? Minus 2 pi squared ks dks du. Let us keep du and not d eta, but I use ks and eta, but we will write the denominator in terms of tau. We use ks and u, and the denominator in terms of tau and eta. You will see why. But anyway, the denominator is tau minus I phi p0 plus ps eta. That's it. So we have to study this kind of singularity. It is a pole, but it has an imaginary part, and so it is it's not singular. If this were 0, you would have dks divided by ks. Basically, that would be singular. This is an integrable singularity. And we studied two possibilities. One is, first we shrink, and then we move from above and from below. And the second one is, first we sit inside, which means we do neglect the Vic rotation, because we do not move from anywhere. And sitting inside, then we deform. There is one thing that here we can, it is a simplified case actually, because one thing that you may notice is that, well, we have to shrink that and to a branch cut, and that can be achieved by means of the deformation. In this case, deformation is a complicated operation, but in this case, the size of this will shrink either if, for example, you set the external space momentum to 0. Because if you can see that if the external space momentum is 0, then P0 is only real. So there cannot be any extension. It has to be already, and in that case you can check it's the correct branch cut. So you can say, okay, but if I'm just choosing a frame, PS, I can always put P equals 0 because we are, remember, everything happens above the threshold, so we can assume P squared positive. But we are working in a non-manifest Lorentz invariant way. So for the moment, let me describe what happens doing this operation instead of the deformation. So we have two cases. Phi goes to 0, then PS goes to 0, or PS 0, then phi 0. So phi going to 0 means that you compute inside, you don't have any Vic rotation, you don't have any phase, you compute there, and then you deform. So you compute with the wrong domain, because this is non-vanishing, PS is different from 0, and then you deform. Instead here, you first deform, and then phi goes to 0. And depending on phi going to plus or minus 0, you are rotating from above or from below. So that are two cases. Phi equals 0 gives you this for phi equals 0. So minus 2 pi squared ks dks du tau minus I ps eta. And then when you take PS going to 0, what do you get? Let me write it to you, and perhaps you will agree with me that what you get is the principal value of 1 over tau plus I pi sine of eta delta of tau. So it's like saying that you have 1 divided by tau minus I epsilon, and you are taking epsilon to 0. But actually, epsilon can have two signs, because eta can be positive or negative. Eta is an angle. Actually, when PS goes to 0, eta is just u, apart from a factor. Eta is just u. You see, when PS goes to 0, and u is a cosine, so it goes from -1 to +1. And eta will go from minus whatever, -10 to +10. It's just a factor here. And when PS goes to 0, you lose this. So apart from the translation and a factor, the integral on Ks is just an integral on d tau. So you get the principal value and you can perform the change of variables. That will be d tau du proportional to that plus I pi, let me check, plus I pi, yes. So in this limit, this eta, the sine of eta is the sine of u, because the coefficient is, this disappears in the limit, so the sine of eta is the sine of u, delta of tau. But in the limit, when PS is equal to 0, there is no dependence on u. When PS is equal to 0, the angle cannot appear anywhere. So the integral in du is the integral of the sine of u from -1 to +1 times n, something that cannot depend, everything else cannot depend on u. So this disappears, and you get something proportional to d tau, principal value 1 over tau. And let me stress that this has no imaginary part. And that shows you that the singularity can be integrated. This is a distribution, well defined. It's not a problem. And this is the result. Let's check what happens when B, we take the case B. So PS goes to 0. That means that we replace PS by 0 there. And so there is no PS. And here it is similar. Let's say that P0 is positive, but now we have to take phi going to 0. And you have a difference in the result depending on whether you take phi to be plus or minus, which means that you go from above or from below. So you will get something proportional to d tau du, and then there will be the principal value of 1 over tau, but then you will have plus or minus, depending on which side you take, delta of tau. It doesn't depend on u, the sign of u, so the integral in du will be trivial. It will give 2. Nothing will depend on u because ps has disappeared. ps has already disappeared from here. And you see that this would be the analog of the Feynman prescription. Actually, this is not a Feynman prescription because we had this pole in the first and third quadrant, so that's an analog of, but there is no Feynman prescription. Feynman prescription is just the analytic Wick rotation from the Euclidean, and there is no analytic Wick rotation here. But anyway, pretty much as you find from the usual Feynman prescription from above or from below, you have imaginary parts. And that means you have a discontinuity, a jump, and the discontinuity is this. But these are the two results from above and from below. If you average them, if you take the arithmetic average of the two, this disappears and you get exactly that. And then you have to take the discontinuity of the arithmetic average, because the arithmetic average will be your amplitude. And that has no discontinuity because it will be real. So the arithmetic average is the way to define the amplitude. Now, this is a very general argument, and although here I have not used the deformation, because in this very simple case of the bubble diagram, you can trade the deformation of that domain by PS. So this is a simple thing that only happens for the bubble diagram. And in more general cases, you have to use the deformation. But now that you understand what happens, it's not difficult to do it. Because basically, let us check what you have here in one dimensions. As we said, every point here, these 2 points, where was it? Probably previously here. For example, B and C, you see, B and C are those 2 points. This point will be this one. If you repeat it, if you do it for every line here, you discover that there is a map between, you see these 2 points are here, so there is a map between the integration domain and this curve. This is a map. So the line goes into that line. And this is, you can use it as a change of variables. And when you make the deformation slowly, you are shrinking this curve, and then little by little, and then when you get to the point, this will become a half line, but a half line that's actually a line, because it comes from minus infinity, it reaches the threshold, and it goes back. So that's what you get. But that you can use as a change of variables for your integral. And if you are in higher dimensions, this is multiplied by a plane, and what you will discover that up to symmetry factors that integrate away trivially, the integration domain, which is now a plane, for example, this line times the vertical line, or this deformed line times the vertical line, it fills the entire region. It's just that. And so you can use it again as a change of variables. And so when you shrink, you make that shrinking, you can phrase it in an explicit way, actually. And then your d3k, well, the integral divided by d phi will go into, you can shrink this, and during the process you will have, let me describe it, just before the ultimate shrinking, you will have a strip. And since this is a change of variables, you will have a d tau. Tau is the integral along the strip. A d eta, which will be, but let's say that d eta has a finite range. So since the strip is shrinking, there will be a factor. And the singularity will have to be the same, or the same form, because that's a pole with an imaginary part. And phi will be still the phase of P0, so it's not much else you can do. With the difference that instead of having PS, this will be just the size of the strip. So you use it as a change of variables, and that will return the same result. Then you can complete the shrinking. PS goes to 0 before the Vic rotation, and then you have two possibilities, from above and from below. And if you average them, you will get the same result as you get when you first, well, you ignore the Vic rotation, you don't do it, you sit in between the strip, and then you take PS going to 0, P tilde S, which means you complete the deformation after calculating there. So that will be still the principal value. What is the moral of the story? The moral of the story is that these unphysical thresholds are crossed, bypassed, I don't know, of the average continuation which is the arithmetic average of the two analytic continuations. And since it is an arithmetic average, now we'll see it in an example, it is not analytic. So for example, let us compute the bubble diagram in phi to the fourth theory. With no mass for the moment. And normal propagators, not higher derivatives, not higher derivative propagators. We start from the Euclidean. This is a normal theory, so we can use the analytic continuation from the Euclidean. We put a cutoff because it's divergent. And so what happens for P small? This is a trick to compute the entire result without making too much effort. So we are in the Euclidean space. So that means that we can use polar coordinates. The integral on the angle is easy. The integral on lambda is also easy. And you have this. This is the divergent part. Let me write it like that. Now, there is no other way. Yes, you already know the result there, because the logarithm must be dimensionless. And so apart from constants, additional constants that can all be hidden inside the cutoff, which will later disappear. So there is always a arbitrariness when you subtract infinity to subtract a constant, plus the constant. But the point is that you already determined the result, because the dependence on the external momentum is what matters here. P. That's in the Euclidean. Minkowski you just make the Wick rotation. P squared becomes minus P squared, but in Feynman prescription, when you have P squared, you rotate from above. And if you rotate from below, you get the complex conjugate. Which means minus or plus. Now let's take the arithmetic average of the two. That is, corresponds to quantize the objects in between. So instead of having plus I epsilon here, what you would do is to take those propagators, you square them, you add that width, which means when the width is non-zero, you have those kinds of issues we have already discussed. You have extended regions, you go inside, you compute inside, and then you take the deformation and so on. In the numerators you don't care because they do not disturb the analysis of the singularities, so you have to use a different prescription. That's like using a different prescription. So the result will just be the arithmetic average. And the arithmetic average of this is what? 1 divided by 4 pi squared logarithm of lambda squared, lambda to the fourth, p squared, squared, 1 divided by 2, or minus p squared squared if you want. Because if you take the average, you would get that kind of thing. Yes, you sum the two things, so have that. That's like saying the logarithm of z, 1/2 logarithm of z squared, if z is minus p squared, or so that means that you have what? You see, what is in the complex z-plane this kind of function? Well, normally, Feynman, you would have the logarithm of z. That is what? A function with the branch cut there. Yes, the function with the branch cut there. Z equal to I epsilon, so it has a small positive imaginary part. And if you take the complex conjugate, you have it here. Or, can do it a little bit better. Let me do it like this. If you take this function, you have a branch cut. Let me deform it like that, because we are interested in the real axis in both cases, but let me deform it like that. I can, because I'm not crossing the real axis, so let me deform it like that. And when you sum those two analytic functions, you break the complex plane into two regions. And that means that you have an analytic function there, then you can move the two branch cuts wherever you want. You can deform them. You can have an analytic function here, which is on the real axis, the logarithm of the absolute value, and on the negative real axis, it will be the same. But you cannot connect them analytically. So then you have broken the complex plane into two, and you have an analytic function outside and an analytic function inside. And if you want, you can deform those two the way you like. You can take them to the strip. You can evaluate your thing inside. You can shrink them later into a branch cut, but you have to remember that you computed the amplitude inside before shrinking, or you can deform it the way you like. you can go back to this funny deformation. It doesn't really matter because the function you get on the other side is analytic. And it is analytic because it is the arithmetic average of two analytic functions. So it is analytic. It's the arithmetic average of two analytic continuations. So the arithmetic average of two analytic continuations is not analytically related to the function outside, but it is still analytic. Not only, but that means you can compute everything in the Euclidean region and reach every other region, and by means of the average continuation. So in our picture, we had this funny thing, but instead of computing on the real axis, which is problematic, it's just compute on the imaginary axis, because now you know what to do. Even normally you know what to do, you just compute in the Euclidean and you do the analytic continuation, which is the Wick rotation. Here you do this non-analytic operation. And by the way, renormalizability is still okay because it is okay in the Euclidean, and once you have renormalized in the Euclidean, you can make arithmetic sums of analytic continuations of convergent functions as much as you wish. They will be still convergent. In 5 minutes, we will discuss unitarity.